Welcome back to the deep dive. When you start really thinking about numbers, it's kind of like peeling back the layers of an onion, you know what I mean? You
Right.
start with just simple counting, right? One, two, three, those natural numbers. Like if you think about solving, say, x plus 2 equals 13.
Right.
Yeah, x is 11. Easy peasy, right?
Yeah.
But then you encounter something like x plus 5 equals 5.
Yeah.
And suddenly we need 0, right?
Right.
And that brings us into this whole world of whole numbers. But then it gets even trickier. What if we had x plus 18 equals 5?
Okay.
And bam, now we need negative numbers. We're talking about integers.
That's right. And, each expansion of our number system kind of gives us the power to grapple with a wider range of problems that we might encounter.
Which, right, exactly, yeah.
But even with integers, as elegant as they are, there's still some roadblocks.
Yeah, yeah.
You think about an equation like 2x equals 3.
Mhm.
There's no integer that really satisfies that perfectly,
Yeah.
right?
Right.
Yeah.
Or what about 5x plus 7 equals 0?
Yeah.
Integers kind of leave us hanging again.
Exactly. It's
Yeah.
like we still need some tools, right?
Yeah.
We need some more tools in our toolbox to be able to really solve all these equations. And that's where, of course, our topic for today comes in. We're talking about rational numbers.
Right.
So for 2x equals 3, right? The
Yep.
solution's 3 over 2.
Exactly.
And for 5x plus 7 equals 0, the solution is negative 7 over 5.
Right.
And all of a sudden, these equations that we couldn't solve before have really nice answers.
Right.
So to be clear for our listener, right, rational numbers are really just fractions.
Yeah.
They're a ratio of two integers, p over q, where q is not 0. We can't have 0 in the denominator.
Exactly.
Yeah.
And for this deep dive, we're not just going to rehash what a fraction is.
Right.
We're going to really try to understand the fundamental properties of how these rational numbers behave. When we add them, subtract them, multiply, divide them.
We're talking about things like closure.
Yes.
We're talking about commutativity, which is like the order of operations.
Right.
Associativity, how we group them, identity elements, and then that interesting distributive property.
Yeah.
And our exploration today is rooted in the very mathematical texts that actually define these foundational rules.
Okay, so let's jump into that first property then. Let's talk about closure. What is closure and why should we care about it?
Think of closure as whether a number system is kind of self-contained under a particular operation.
Mm-hmm.
So if you perform that operation on any two numbers within that system, will the result always stay within that same system?
Okay.
So if we start with whole numbers,
Right.
so that's 0 and all the positive integers. If you add two whole numbers together, say 3 and 7, you get 10. Still a whole number.
Right. Right.
If you multiply them 2 and 5, you get 10.
Mhm.
Still a whole number. So whole numbers are closed under addition and multiplication.
Okay, that makes sense. It's kind of like we're staying within the walls of the whole number world, but the text points out that they're not closed under subtraction. So why is that a problem?
Well, imagine you have, say, 5 apples,
Okay.
and someone comes along and asks for 7 apples.
Uh-oh.
If you're only dealing with whole numbers, there's no way to represent that outcome,
Yeah.
right?
Yeah. Yeah.
Mathematically, 5 minus 7 gives you negative 2,
Right.
which is an integer, but it's not a whole number.
Right. Right.
So that subtraction took us outside the kind of that closed set of whole numbers.
Right. We have to venture out into the negative territory.
Right. And what about division for whole numbers? Does that keep us within the whole number world?
It definitely doesn't consistently, right? So if you divide 6 by 2, you get 3, which is a whole number.
Right.
But if you divide 5 by 8, you get 5 over 8, which is a rational number, but it's clearly not a whole number.
Right. So division it often leads us out of that whole number system.
Okay, so closure really depends on the specific number system we're talking about and what operation we're performing on those numbers. So what happens when we take a step up the ladder and we go to integers? How do integers hold up when we think about these operations?
So integers, right?
Yeah.
Positive and negative whole numbers,
Mm-hmm.
including 0. They're a bit more robust in terms of closure.
Okay.
So if you add any two integers, say negative 4 and 9, you get 5, which is still an integer.
Okay.
Subtraction's also closed for integers.
Mhm.
10 minus 3 is 7. Even 3 minus 10 is negative 7,
Right.
both integers. And multiplication works as well. Negative 6 times 4 is negative 24. Negative 2 times negative 8 is 16. all within the integer family.
So integers are definitely an upgrade in terms of closure compared to whole numbers. Where do they still have their limits though? Where do we run into problems?
Uh, just like whole numbers, integers stumble with division. So if you divide 7 by 2,
Yeah.
you get 3.5,
Right.
which is a rational number,
Yeah.
but it's not an integer.
Yeah, that decimal, that fraction
Yeah,
takes us outside.
exactly. Takes us outside the set.
All right, so finally, let's get to the stars of our show today. Let's talk about rational numbers. Are rational numbers closed under these basic operations?
Yeah. So this is where things get really interesting.
Right. Yeah.
So the texts confirm that rational numbers are closed under addition.
Okay.
For instance, if you take, let's say, -3/8, and you add 5/7, you get 19/56, which is definitely a rational number. It's a fraction.
Right.
Subtraction also keeps us within the rationals.
Hmm.
You know, 5/7 minus 2/3 equals 1/21. Again, another rational number.
Yeah.
And multiplication, too.
Yeah.
If you multiply -2/3 by 4/5, you get -8/15, which is still a rational number. So the crucial takeaway here is that the sum, the difference, and the product of any two rational numbers, you're always going to get another rational number. It's like the rational number system is is kind of self-sufficient when it comes to these three operations.
Right. It's a big step. It's a big step up in terms of being able to stay within our number system. So what about division for rational numbers? Is that the final piece of the puzzle?
Almost.
Okay.
So the texts are careful to point out that rational numbers are not closed under division in one specific case,
Okay.
and that's division by 0.
Right.
Dividing any number by 0 is undefined. It's a mathematical no-go zone.
Right.
But, and this is a key distinction, if you exclude 0 from the set of rational numbers, then the set of all non-zero rational numbers is closed under division.
Okay.
So if you divide any non-zero rational by another non-zero rational, you'll always get another non-zero rational number.
Okay. Okay. So that zero exception, that makes sense, right? You can't divide by nothing. So the source material has this table that kind of summarizes all this information for rational numbers, integers, whole numbers, and even natural numbers across addition, subtraction, multiplication, and division. And maybe as we talk about these remaining properties, it would be good for you, the listener, to think about how those properties also apply to these different number systems, right?
That's a fantastic idea. I think it'll really help to solidify how these properties distinguish these sets of numbers, but also how they connect them.
Yeah, exactly. All right, so next up, we're going to talk about the commutativity property.
Okay.
So what's the core idea behind commutativity?
So commutativity at its heart is
Right.
all about order.
Okay.
So does the order in which you perform an operation on two numbers, does that affect the final result?
Okay.
If it doesn't, then that operation is commutative.
So let's ground this with some examples. Let's start with our familiar whole numbers.
Sure.
So how does commutativity work when we're just talking about whole numbers?
Okay, so for whole numbers, addition is commutative.
Okay.
So 2 plus 5 gives you 7, and 5 plus 2 also gives you 7. So the order there doesn't matter.
Right.
Same with multiplication, right?
Yeah.
3 times 4 is 12, 4 times 3 is 12. But subtraction is a different story, right?
Yeah. Yes.
7 minus 3 is 4. The 3 minus 7 is -4. So the order flips the sign of the result.
Yeah.
And division's also not commutative.
Right.
8 divided by 2 is 4, while 2 divided by 8 is 1/4.
Right. So different outcomes.
Totally different outcomes.
Yeah. So for subtraction and division of whole numbers, the order we perform the operation really does have an impact.
It matters.
Yeah. So what about integers? Do they follow the same rules when we think about commutativity?
They do. They do.
Yes.
So addition and multiplication are commutative for integers. So for example, -5 plus 2 is -3. And 2 plus -5 is also -3.
Right.
And -3 times 6 is -18, just like 6 times -3. However, just like with whole numbers, subtraction and division are not commutative for integers.
Okay.
So the text points out that 5 minus -3 is 8, while -3 minus 5 is -8.
Right.
Again, the order changes the result.
Yeah. So it seems like we're seeing a little bit of a pattern emerge here. So what about our rational numbers? Do they also follow this trend when we're thinking about commutativity?
Yes. So for addition and multiplication, rational numbers are also commutative.
Okay.
So the text has a really clear example. Negative 2 over 3 plus 5 over 7 equals 1 over 21. And if you reverse the order, 5 over 7 plus negative 2 over 3, that also equals 1 over 21. So for any two rational numbers, a and b, a plus b equals b plus a.
Right. Oh,
And
yeah.
the same holds true for multiplication. Negative 7 over 3 multiplied by 6 over 5 is negative 42 over 15.
Okay.
And if you switch it up, 6 over 5 multiplied by negative 7 over 3, you still get negative 42 over 15. So a times b equals b times a.
Okay, so that holds across the board.
Yep.
What about subtraction and division when we're dealing with rational numbers? Do they also lack this commutativity property?
Absolutely. Just like with integers and whole numbers, subtraction and division are not commutative for rational numbers.
Okay.
And, since integers are themselves rational numbers, right?
Yeah.
And we already saw that subtraction isn't commutative for integers, like 2 minus 5 isn't the same as 5 minus 2, then it stands to reason that it won't be commutative for all rational numbers either.
Right, right.
And division, if you take negative 5 over 4 divided by 3 over 7, you'll get one result. But if you flip it, 3 over 7 divided by negative 5 over 4, you'll get a different result.
Right.
So the order matters.
Okay, so the commutative property holds for addition and multiplication in whole numbers, integers, and rational numbers, but not for subtraction and division
Correct.
in any of them. So that's a good pattern to recognize there. Now let's move on to the associativity property. So what's the main idea behind associativity?
So associativity really comes into play when you have an expression with three or more numbers, right?
Okay.
And the same operation. And it's about whether the way you group those numbers using parentheses affects the final outcome.
Okay.
So, yeah.
So let's break that down. Let's start again with our foundation of whole numbers. How does associativity work when we're dealing with whole numbers?
Okay, so for whole numbers, addition is associative.
Okay.
So if you have a plus parenthesis b plus c, close parenthesis, the same as open parentheses, a plus b, close parenthesis, plus c.
Okay.
So for example, 2 plus, open parenthesis, 3 plus 4, close parenthesis, that's 2 plus 7, which is 9.
Right.
And if you group it as open parenthesis, 2 plus 3, close parenthesis, plus 4, you get 5 plus 4, which is 9.
Right.
So the grouping didn't change the sum.
Right.
Same idea for multiplication.
Okay.
So a times open parenthesis, b times c, close parenthesis equals open parenthesis, a times b, close parenthesis, times c.
Okay.
Take 3 times, open parenthesis, 5 times 2, close parenthesis. That's 3 times 10 equals 30.
Right.
And open parenthesis 3 times 5,
Yeah.
close parenthesis times 2, that's 15 times 2 equals 30. Again, the grouping doesn't affect the product.
So for those two operations, it's almost like we can rearrange those parentheses, and it doesn't change the outcome of the calculation at all. So what about subtraction and division with whole numbers? Are they also associative?
They are not associative.
Okay.
So for subtraction, consider 5 minus, open parenthesis, 7 minus 3, close parenthesis.
Okay.
So that's 5 minus 4, which equals 1. But if you group it as open parenthesis, 5 minus 7, close parenthesis, minus 3, you get negative 2 minus 3, which is negative 5.
Right.
So different results depending on how you group.
Right.
And division also lacks associativity. Think about it. Open parenthesis, 12 divided by 3, close parenthesis, divided by 2. That's 4 divided by 2, which is 2. But if you calculate 12 divided by open parenthesis, 3 divided by 2, close parenthesis, that's 12 divided by 1.5, which is 8.
Right. So again, different outcomes depending on how we group.
Different outcomes.
So those parentheses, they definitely matter for subtraction and division when we're dealing with whole numbers. So what about when we step up again and we go to integers? How does associativity work with integers?
Integers actually follow the same pattern as whole numbers when it comes to associativity.
Okay.
So addition and multiplication are associative.
Mm.
The text gives the example, negative 2 plus open bracket, 3 plus negative 4, close bracket. That simplifies to negative 2 plus negative 1, which is negative 3.
Yeah.
And if you group it as open bracket, negative 2 plus 3, close bracket plus negative 4, you get 1 plus negative 4, which is negative 3. So the sum is the same.
Right.
Multiplication also holds. However, just like whole numbers, subtraction and division are not associative for integers.
Okay.
The example there, 5 minus open parenthesis, 7 minus 3, close parenthesis equals 1, well, open parenthesis 5 minus 7, close parenthesis minus 3 equals negative 5.
Right.
So again, grouping changes the outcome.
Yeah, it's quite a consistent theme we're seeing here. So
Mhm.
so what about rational numbers? Do they continue this pattern when it comes to associativity?
They do. They do.
Yeah.
So addition and multiplication are indeed associated for rational numbers. And the text walks us through this example for addition.
Mm.
So -2 over 3 plus, open parenthesis, -3 over 5 plus 5 over 6, close parenthesis. So first you calculate what's inside the parenthesis.
Right.
-3 over 5 plus 5 over 6 equals -18 over 30 plus 25 over 30, which is 7 over 30. The -2 over 3 plus 7 over 30 is -20 over 30 plus 7 over 30, which gives you -13 over 30. Now, if you group it as, open parenthesis, -2 over 3 plus -3 over 5, close parenthesis, plus 5 over 6.
Okay.
So you get -10 over 15
No.
minus 9 over 15, close parenthesis, plus 5 over 6.
Right.
That's -19 over 15 plus 25 over 30. That's -38 over 30 plus 25 over 30, which also gives you -13 over 30. So the result is the same, regardless of the grouping.
Similarly, for multiplication, one example given is -7 over 3 times, open parenthesis, -5 over 4 times 2 over 9, close parenthesis. So first, -5 over 4 times 2 over 9, that gives you -10 over 36, which simplifies to -5 over 18. Then -7 over 3 times -5 over 18, that gives you 35 over 54. Now, if you group it as, open parenthesis, -7 over 3 times -5 over 4, close parenthesis, times 2 over 9, you get 35 over 12 times 2 over 9 equals 70 over 108, which simplifies to 35 over 54. So A times, open parenthesis, B times C, close parenthesis, equals open parenthesis, A times B, close parenthesis, times C does hold.
Okay, so that's a really nice confirmation
Yeah.
of the pattern we've been seeing. So addition and multiplication really do seem to have this flexibility, right? In
Yeah.
terms of how we group things. What about subtraction and division of rational numbers? Do they also lack this associativity property? Absolutely.
Yeah.
Just like with integers and whole numbers, subtraction and division are not associative for rational numbers. The text even gives a specific example for division. So open parenthesis, -1 over 2 divided by -1 over 3, close parenthesis, divided by 2 over 5. That's not equal to -1 over 2 divided by, open parenthesis, -1 over 3 divided by 2 over 5,
Mm.
close parenthesis. And let's just go through the calculation really quickly.
Yeah.
So open parenthesis, -1 over 2 divided by -1 over 3, close parenthesis, divided by 2 over 5. That gives you 3 over 2 divided by 2 over 5, which equals 15 over 4.
Mhm.
Now -1 over 2 divided by -5 over 6, which is 3 over 5. And clearly 15 over 4 is not the same as 3 over 5.
Right.
So again, the way we group the operations really changes the outcome.
Okay, so that consistent lack of associativity for subtraction and division across all these number systems, that is pretty telling. All right, let's move on and talk about identity elements. So what is an identity element?
Okay, so think of an identity element as this special number that when combined with any other number in the set using a particular operation, it leaves that other number unchanged,
Okay.
like a neutral element for that operation.
Okay.
You
So
know,
so let's start with addition. So what would be the additive identity?
Right.
So what number can we add to any other number and not change its value?
so the additive identity is 0.
Okay.
So if you add 0 to any whole number, like a +0, you just get it back.
Right.
The same holds true for any integer. B plus 0 equals B.
Right.
And for any rational number, C plus 0 equals C.
Okay.
So, the text gives us the example, -2 over 7 plus 0 is just -2 over 7.
Right.
0 has no effect on the value when added.
So 0 is this universal additive identity across these different number systems.
Exactly.
Yeah, that's pretty fundamental.
Yeah.
So what about the multiplicative identity? What number can we multiply any other number by and still get the original number back?
So that role is played by 1.
Okay.
If you multiply any whole number by 1, A times 1 equals A.
Right.
Any integer by 1, B times 1 equals B.
Right.
Or any rational number by 1, C times 1 equals C, you get that original number back.
Okay.
And the text shows us this. -2 over 7 times 1 is still -2 over 7.
Right.
And also 3 over 8 times 1 is 3 over 8. So 1 is the multiplicative identity for rational numbers, integers, and whole numbers.
Okay, so that's That's, again, pretty straightforward
Yeah,
and pretty essential to our mathematical toolkit.
right.
Now the source brings up this interesting point. It says, if a property holds for rational numbers, will it always hold for integers and whole numbers? So
Yeah.
what do you think about that?
That's a really, really insightful question. And the answer is, integers and whole numbers are subsets of rational numbers,
Right.
which means that if a property is true for all rational numbers, it has to also be true for any integer or whole number,
Right.
because those are just specific types of rational numbers.
Right.
So, for example, since addition is commutative for all rational numbers, it's automatically commutative for integers and whole numbers as well.
Right.
But the reverse isn't necessarily true. A property might hold for integers, but not for all rational numbers.
Okay.
Although we haven't really seen a clear example of that with these basic properties.
Right.
More importantly, a property might not hold for a smaller set,
Yeah.
like integers, but does hold for the larger set of rationals in a specific way.
Right.
So think back to closure under division.
Right. Yeah. Yeah.
Yeah, excluding zero.
Yeah, exactly. So there's this nested relationship between these different number systems
Oh,
where rational numbers are really the most encompassing of the sets that we've talked about so far.
Right.
All right. So let's move on to our final core property. That's distributivity.
Okay,
So what's the essence of the distributive property?
Okay, so distributivity really describes how multiplication interacts with addition and subtraction.
Okay.
So the distributive property of multiplication over addition states that if you have a number multiplied by the sum of two other numbers, like 8 times open parenthesis b plus c, close parenthesis, it's equal to multiplying the first number by each of the other two individually and then adding the results. So open parenthesis, a times b, close parenthesis, plus open parenthesis, at times c, close parenthesis.
Okay.
And the same principle applies to subtraction. So a times open parenthesis, b minus c, close parenthesis, equals open parenthesis, a times b, close parenthesis, minus open parenthesis, a times c, close parenthesis. And this property it's really fundamental, and it holds true for rational numbers.
Okay. So can you walk us through an example from the text so we can see this in action?
Absolutely. So the text shows us negative 3 over 4 times, open parenthesis, 2 over 3 plus negative 5 over 6, close parenthesis.
Okay.
So first they simplify what's inside the parenthesis.
Okay.
2 over 3 plus negative 5 over 6 becomes 4 over 6 minus 5 over 6, which equals negative 1 over 6. Then they multiply. Negative 3 over 4 times negative 1 over 6 gives us 3 over 24, which simplifies to 1 over 8. Now let's look at the distributive side. So open parenthesis, negative 3 over 4 times 2 over 3, close parenthesis, plus open parenthesis, negative 3 over 4 times negative 5 over 6, close parenthesis, equals negative 6 over 12 plus 15 over 24. Simplifying those fractions, we get negative 1 over 2 plus 5 over 8. And finding a common denominator, that's negative 4 over 8 plus 5 over 8, which also equals 1 over 8.
Right.
And since both sides of the equation result in the same value, it really demonstrates the distributive property quite nicely.
Yeah, it's a really, really clear way to see how that multiplication distributes over the addition, and in this case with a negative number as well. The source also has a couple try these examples for you, the listener, to kind of play around with. So we have negative 7 over 5 times, open parenthesis, 3 over 12 plus 5 over 12, close parenthesis, and open parenthesis 9 over 16 times, open parenthesis 4 over 12 plus negative 3 over 9, close parenthesis. So those look like some good practice problems to kind of help solidify this concept.
Yeah, definitely worthwhile exercises to try.
Yeah. Yeah. And the text even has an example 3. So negative 2 over 5 times negative 3 over 7. Minus 3 over 7 times negative 3 over 5 times 1 over 14. And this example is interesting because it shows how you can use both the commutative property and the distributive property.
Right.
To rearrange the terms, to kind of simplify the calculation by swapping the order of some of the factors and then factoring out that common negative 3 over 7, the problem becomes much more manageable.
Exactly.
So it's really interesting to see how these properties are not just these abstract rules, right? They're actually powerful tools that we can use to really simplify and be more efficient in how we solve these mathematical problems.
Yeah, absolutely. They provide the very foundation for algebraic manipulation and and a deeper understanding of how numbers work.
Okay, so just to kind of bring it all together, we've taken a really good look at closure.
Yeah.
Whether operations keep us within a specific number system, we talked about commutativity, whether the order matters.
Right.
And
Associativity, whether grouping matters.
right.
We talked about the really essential role of 0 as the additive identity and 1 as the multiplicative identity.
Yep.
And then finally, this distributive property of multiplication over addition and subtraction for rational numbers.
Yeah. I think that's a really nice comprehensive overview of these core properties.
Yeah, and the text also briefly mentions the density property of rational numbers,
Right.
which is this amazing idea that between any two distinct rational numbers, you can always find infinitely many other rational numbers.
It's pretty incredible when you think about it.
It is, yeah. It's kind of mind-boggling.
Yeah.
We didn't really have time to go into examples of that today.
Yeah.
But it's another really key characteristic of what makes rational numbers, you know?
It is. You think about between 1/2 and 2/3, you could have 5/12, you could have 7/16,
Yeah.
and just on and on and on. Right? Infinitely many.
Infinitely many.
Yeah, yeah. So it really does make you think about just how much richness there is.
Yeah.
Even within these number systems that seem pretty simple.
Right.
Maybe a topic for another deep dive.
Indeed. Yeah.
So as we conclude this exploration into the fundamental properties of rational numbers, it really does highlight, I think, how our need to solve these increasingly complex equations
Yeah.
has really driven the expansion of our mathematical toolkit
Right.
from those initial natural numbers